All right, let's talk about liquids. I want to talk about properties of the liquid state. Now, when you think about liquids, I want you to think about the molecules in those liquids in packed random motion. So remember, liquids are a condensed phase, so the molecules are packed pretty closely together, but they're moving around a whole lot. So we have constant random motion in the liquid phase. So as we talk about each of these properties, I want you to think about those molecules being kind of packed together, but still having the liberty to move around. The first property I want to talk about is viscosity. You might have heard of viscosity. The adjective is viscous. And when I think of viscosity, the question to ask is how well does it flow? So, viscosity can be defined as resistance to flow. Molasses has very high viscosity. Syrup has very high viscosity. They don't want to flow. The molecules are very attracted to each other, so they are resistant to flow. So, viscosity is very much due to the attractive intermolecular forces, the attractive forces holding the molecules together. The stronger the attractive forces, the higher the viscosity. Okay, because the stronger the intermolecular forces are, the more the molecules want to stick to each other rather than flow. So, a couple of questions I would like to ask you. As the temperature rises, what do you suppose happens to viscosity? So, as temperature rises, what happens to viscosity? So now we need to think a little bit about, well, this might harken a little bit back to the kinetic molecular theory of gases, but in general, what happens to particles when temperature starts to rise? They move faster, right? As temperature goes up, molecules start moving faster, and the faster motion means that they're going to flow easier, right? So as temperature rises, flow is going to be facilitated. So what happens to viscosity? Well, viscosity decreases, right? As temperature goes up, viscosity decreases because the molecules start moving faster. And when they move faster, they flow easier. So they move faster, therefore they flow easier. So at higher temperatures for a given compound, viscosity is going to decrease. Now, another thing we can do is compare different molecules and predict which is going to have higher viscosity. So, which compound has higher viscosity? CH3, CH2, CH2, CH3. Okay, this is a hydrocarbon called butane. Or CH3, CH2, CH2OH. This is an alcohol called propanol. Now, for you guys, the names don't matter, but what matters is their polarity. So butane, like any hydrocarbon, is going to be nonpolar. And the strongest type of intermolecular forces that can possibly exist in a nonpolar molecule are the London dispersion forces, LDF. Propanol, by contrast, is an alcohol. And this end of the molecule here, where the O is directly bonded to the H here, that means that this molecule is going to be capable of hydrogen bonds. It's highly polar because the oxygen is directly bonded to an H. So that gives rise to much stronger intermolecular forces than the London forces. So this is definitely going to be more viscous. Let's see if I can spell viscous properly. Viscous. I think that's the way you spell it. So the stronger the intermolecular forces, the more viscous the compound is going to be. And that's because you have very strong intermolecular forces holding the molecules together. So it doesn't want to flow. Okay, so this is no contest between butane and propanol. Propanol is going to be much more viscous because of its hydrogen bonds. Another similar property of the liquid state is surface tension. If we define viscosity as resistance to flow, surface tension is very similar, but think of it as resistance to spreading. So when you think about surface tension, the best example is to think about water droplets forming beads. For example, on a waxed car, water droplets will bead up, right? That beading that water does is a property of surface tension. Water also forms a meniscus. If you put it in a graduated cylinder, for instance, it forms a meniscus. And that is, again, because of surface tension. So it's a resistance to spreading. The technical definition is as a measure of the inward force on a liquid surface. So on Blackboard, I'm going to post a pretty nice YouTube demonstration video of surface tension. And if you want, you can just play with water and try to make it bead up. If you play with water and say rubbing alcohol, you can see that rubbing alcohol will spread very easily compared with the water because water has greater surface tension. Now, as like with viscosity, as the intermolecular forces get stronger, surface tension, well, it's kind of the opposite, right? As intermolecular forces get stronger, surface tension goes up because it's a resistance to spreading. So, which has the smaller surface tension out of these three choices? Which has the smallest surface tension? Water, acetonitrile, or methanol? Okay, so the names, once again, are not important. What's important are the chemical formulas and telling whether they're polar or not, acetonitrile or methanol. So we have to look at whether these molecules are polar. And I've also posted videos that kind of give you a review of polarity. So if you need to review how to tell if a molecule is polar, you should go back and review that. So water. All right, well, water is certainly going to be full of hydrogen bonds. Acetonitrile, well, there are hydrogens in it, but they're not bonded to the nitrogen. The hydrogens are bonded to the carbon. So this part of the molecule, though, definitely has a dipole, right? Because nitrogen's very electronegative. So this is going to be a polar molecule, but the strongest intermolecular forces here are going to be the dipole-dipole forces rather than the hydrogen bonds. We don't have any hydrogen bonds there because hydrogen's not directly bonded to the H. In methanol, however, we do have hydrogen bonds because the hydrogen is bonded to the O. So looking at the three of these, the one with the weakest forces is going to have the smallest surface tension. So that is going to be the acetonitrile. Weakest forces, smallest surface tension. So the dipole-dipole are the weakest forces. This is going to have the smallest surface tension out of the lot. Now, we can also think about vaporization. And I'm going to talk a little bit about this here and also in the next video that I do, because vaporization is something that is going to relate to vapor pressure and boiling point and everything else. Okay, well, what is vaporization? It's a change of state. Vaporization is the process where liquid goes to gas. And the molar heat of vaporization is defined as delta H vap. Delta H, you may recall, is the change in enthalpy. So the enthalpy of vaporization, delta H vap, is literally defined as the amount of heat required to vaporize 1 mole of liquid. It is an endothermic property, okay? The heat of vaporization is endothermic. Endo means in, thermic means heat. So you have to put energy in to vaporize something. I hope that makes sense. Now, I want you to think about vaporization for a second and kind of how it works. For example, if you're trying to boil something. If you try to boil something, you raise the temperature, right? So what happens as temperature increases? Well, as temperature increases, like we said before, molecules start to move faster. And as molecules move faster, intermolecular forces get disrupted. Intermolecular forces break. I'm going to say they're disrupted. And then finally, eventually, the molecules go to vapor. So if you're trying to boil a liquid, you're raising the temperature, the molecules start moving faster, the intermolecular forces get disrupted, and eventually the molecules are going to go into the vapor phase. Okay, so that seems pretty obvious. Let's think about the molar heat of vaporization for water. Like I said, it's an endothermic property. So we're thinking about 1 mole of liquid water going to 1 mole of gas. That's not a chemical reaction, that's a physical phase change. For water, the heat of vaporization is positive. Remember, it's endothermic, 43.8 kilojoules per mole. Now, the stronger the intermolecular forces, the larger this number is going to be. Water is very polar, it has hydrogen bonds, so it has a pretty high heat of vaporization. If you had a nonpolar molecule, it would be apt to have a lower heat of vaporization because it would have less strong intermolecular forces to break in order to be vaporized. So you can kind of, I should also say that we could think about the opposite process, right? Condensation of the gas to the liquid. And we could have a molar heat of condensation. Now, your instinct from thermodynamics last term should tell you what that would be. It's just equal and opposite. It would be the exothermic minus 43.8 kilojoules per mole. Okay, so this is going to be the heat that's lost on going from the gas phase to the liquid phase. Okay, so you should be able to look at different molecules and predict the relative heat of vaporization based on their polarity, like we've been doing for surface tension and viscosity. So out of these 3 choices, which compound has the largest heat of vaporization? Water, H2O, H2S, or H2SE? So these molecules all have analogous molecular structures, right? If you draw out their Lewis structures with some geometry, since these are all group 16 elements in the center, they're all going to look pretty similar. And they're all going to be polar. However, which is the most polar, right? All of these are going to be polar. We're going to have bond dipoles and overall dipole moments and lots of polarity in each one because hydrogen's a very electropositive atom. So if we want to know which has the largest heat of vaporization, we need to know which has the strongest intermolecular forces. Now, out of all of these, oxygen is going to be the most electronegative central atom. So when hydrogen's directly bonded to the oxygen, we have hydrogen bonds. Whereas for these 2 molecules, they're polar, sure, but the strongest forces that exist in both of these are going to be dipole-dipole because we don't have hydrogen bonded to F, N, or O. So that means that if we're thinking about the largest heat of vaporization, water is going to be the one because water's hydrogen bonds means that it is going to require the most heat to vaporize per mole. Okay, so I hope that makes sense. In the subsequent lecture, we're going to talk about vapor pressure and boiling points.